Let's study 9th standard ICSE Physics, Chapter 9, Current Electricity, Section A, the electric current. Current is of two types, the direct current and the alternating current. DC is seen in this diagram. We have a dry cell. This is the positive terminal and this is the negative terminal, the zinc case that is. And current always flows from the positive terminal to the negative terminal. So you can see the direction never changes. It won't go reverse. And then the bulb will glow as long as the switch is on, because that means the circuit is closed. If you switch off this circuit, that means you're breaking the circuit. There will be an air gap in between and current can't flow through air because air is a bad conductor of electricity. Note that the current is assumed to be flowing from higher potential, which is positive, to a lower potential, which is negative. But the truth is, in this case, electrons are actually moving from the negative terminal towards the positive terminal. So the flow of electrons is opposite to the flow of conventional current. This is because when electricity was discovered and theories were established, at that time it was assumed that some positive charge is flowing from a higher potential to a lower potential. Just like heat flows from a hot object to a cold object, or any object falls from a higher altitude to a lower altitude due to gravity. Similarly, it was theorized that current electricity flows from a higher potential to a lower potential. But later, we discovered that actually no positive charge is flowing here. Protons don't move. It is the electrons which travel from the negative terminal to the positive terminal. The negative terminal has excess electrons. Electrons are negatively charged. That is why it is called a negative terminal with excess negative charge comparatively. The positive terminal has comparatively lesser electrons. It has a deficiency of electrons. That is why it is called a positive terminal. So you can imagine if this area has less electrons and comparatively more protons, so it will be more positively charged. So there is a potential difference between them. If you have two tanks filled with water, one has more water and the other has less water, this is called higher potential. This is a lower potential. There is a potential difference. If you connect it with the pipe, the water will flow from the higher potential to the lower potential till the time both of them have the same water level. I'm not talking about water volume, I'm talking about water level. And then they will be in equilibrium and the flow will stop. Similarly, as long as equilibrium is reached, the flow will continue. Excess electrons are going here because there is deficiency of electrons. And this potential difference is created due to some chemical reactions happening inside the dry cell. Once that chemical energy is used up, then electricity can no longer be produced. So if it's a primary cell, you'll have to throw it out because it can't be recharged. If you look at the parts of a cell, you go just smash a AA cell or a AAA cell, and you will see some paste inside it and some black carbon rod inside. That is called the electrode. And the chemical paste surrounding it is called the electrolyte. And thanks to the chemical reactions inside, we can convert the chemical energy into electrical energy as long as the circuit is completed. Some cells are secondary cells. That means they can be recharged. Now let's study the difference between a primary cell and a secondary cell. Secondary cells are also called storage cells. Remember, a cell is singular. If you have many cells connected together, it is called a battery. Now here the chemical reaction is irreversible. That's why we can't recharge it. But here the chemical reaction is reversible, which means if all the chemical energy has been converted into electrical energy, let's recharge it to do the reversible chemical reaction. So once again, we can store the electrical energy in the form of chemical energy inside it. And once it is totally recharged, we can start using it once again. So once again, the chemical energy stored inside it will be converted into electrical energy, and so on and so forth. Can you think of an example of such rechargeable cells? Your phone batteries, the acid lead accumulators in the cars or vehicles, those are all secondary cells because we can recharge them. Another difference is that in primary cell, the internal resistance is quite high. Resistance, as the name suggests, is the hurdle which electricity has to face while flowing. So in this wire, if you imagine the electrons moving, you can imagine that they will collide with these atoms and positive ions and other electrons in their path. That is resistance. Metals have very low resistance. That is why they can conduct electricity very well, and a lot of current can flow through it. Non-metals or insulators are called so because they have very high resistance. So there are too many collisions, and a lot of electricity can't flow through it very easily. So now you know that the amount of current flowing through any metal wire or any substance depends on a few factors, like how good a conductor it is, which of course depends on its resistance. More resistance means less of a conductor it is. It also depends on the potential difference. If there is a great difference, more current will flow. Here the difference is less, so there will be less flow of water. Similarly, we see there is a potential difference. This object has deficiency of electrons. This object has excess of electrons. Surprisingly, we call this as at low potential, a negative terminal, and the deficiency of electrons, well, this becomes at a high potential, that is positive terminal. So by convention, when we draw the arrows for current in a circuit, in any diagram, it's always from high potential to low potential. But remember, the electrons are actually flowing from this low potential with excess electrons to the high potential with deficiency of electrons, so that it is equalized, just like the water is equalized between the two tanks. So we will study more about this in section B. But right now I just wanted you to be aware of the basic terminologies. So section A, let's continue with primary cell and secondary cell. So now you know what is the meaning of resistance. So it seems that the primary cell has more internal resistance. Internal means in the cell, inside the battery. External resistance means in the wire, in the copper wire or any other wire. Secondary cells have low internal resistance. That means less hurdles, and hence they can provide high current as well, which is not possible in primary cells. However, primary cells are light and cheap, so for small electronic devices like your remote or some toys or your watch, primary cells are sufficient. Secondary cells are heavy and costly, especially the ones used in vehicles. Examples have to be learnt. Now, we know the concept of electric current, but mathematically, current is defined as amount of charge per unit time. That means in 1 second, how much charge is flowing through a cross section normal to the direction of the current. For example, if this is a wire, and if I take a cross section, which is a circular cross section here, and we have all these electrons flowing through this cross section, which is a normal cross section. Don't cut a inclined slice, cut a straight slice perpendicular to the direction of electricity. So if we calculate the total amount of charge flowing through this cross section in 1 second, then we know how much current is flowing. Charge is calculated with the help of a unit called coulomb. 1 electron's charge is extremely small. It's just 1.6 into 10 raised to minus 19 coulomb. That's infinitesimally small. But imagine billions and billions of electrons flowing through a wire. So if you accumulate them, then the charge is quite significant. And if you divide it by the time, we get current. And the unit for current is ampere. So when 1 coulomb of charge flows through a cross section in 1 second, we say that the current flowing is 1 ampere, which is nothing but 1 coulomb per second. This is the SI unit, ampere. Now we know that charge is also total number of electrons into the charge of 1 electron. So 1 electron's charge we know, and imagine that there were 10 electrons flowing at a time. So what is the total charge flowing? This multiplied by 10. So charge is N into E. If you substitute this, we get a new formula that current is equal to NE upon T. Interestingly, current in an electrolyte doesn't flow because of electrons, but because of ions. For example, here in the wire, we know that electrons are flowing. But what about inside? Even inside, the current should be flowing to complete the entire path. But inside, we don't have a wire. We have electrolyte, which could be liquid or a paste-like substance, a chemical substance. And there, current flows in the form of ions, cations and anions. The cations are positively charged, so they will be traveling towards the negative terminal, and the anions are positively charged. anions are negatively charged. So they will be going towards the positive terminal. So in the wire, electricity flows because of electrons, but in an electrolyte, electricity flows because of ions. Another difference is that in the wire, metallic wire, the electrons move in a single direction, but it's unidirectional. But in an electrolyte, the ions are moving in two directions. Cations have a different direction and anions move in an opposite direction. So that's called a bidirectional, two directions out there. Also, the current in our household sockets is not DC like this one. It's marble. It's a marble because it's AC, which is far more efficient than DC. You'll study more about AC or alternating current in 10th standard physics. And the story goes that there was a time when there was a competition between Edison and Tesla. Edison supported DC to be used at large scale, and Tesla supported AC on a large scale for households. This is decades ago when electricity had just been discovered. And ultimately now we can see that Tesla has won because his original design for AC generator is being used in the entire world. Why is AC better? That is not in the scope of 9th standard. You'll study this in 10th standard. But just to explain why is AC different, here in DC we have a fixed positive and negative terminal. But in AC, the polarity keeps switching. So the flow of current changes from here to here, then back again in the opposite direction. In fact, it changes around 100 times in 1 second. That's the frequency of electricity in India is 50 Hertz. But again, we don't have AC in the current syllabus. This was just some additional information I wanted you to know. We should know the smaller units of ampere as well. Microampere, milliampere. Now mark the definition of alternating current, in which the magnitude and the direction keeps on changing. Magnitude means the value. If you say the current is 2 ampere, in AC it's not fixed. It's 2 ampere, then 2.5, it becomes 1.5. It keeps fluctuating. But you just have to remember the definition, nothing else. And of course, some additional information. The frequency of alternating current from our mains, that is in India, it is 50 Hertz. Now when we draw circuit diagrams, there are certain symbols you should be aware of. A single cell is shown like this. The bigger line is the positive terminal and the smaller line is negative terminal. So even if you don't write plus and minus, it's okay. But it should be clearly shown that there is a bigger line and a smaller line. And remember, the current always is shown to be flowing from the bigger line, that is positive terminal, to the smaller line, that is the negative terminal. If you have many such cells together, it's called a battery. Remember, the big and the small lines should be alternating. And if it's an AC source, alternating current, it doesn't have any fixed positive and negative terminals. So we show it like this. So instead of a battery, if you are plugging the device into the socket of your mains, then we say we are using an AC source. Then we can't really show the direction of current because it'll keep changing, sometimes clockwise, sometimes anti-clockwise, it keeps changing. Now what about the key? Well, if the key is open, plug key is open, it's shown like this. If it is closed, then we just put a dot in between. When we say the key is closed, it simply means that there is no air gap in between. The circuit is complete, electricity will flow, equipment will work, that is, a bulb will glow. If it's a switch, then this is the off position and this is the on position. If it's a tapping key, which you just press on and off, then this is the off position. Notice that it is not touching the wire here, and this is the closed position. Next, what about resistance? How do we show that? I've already explained to you what is resistance. More the resistance in a circuit, less current will flow through it. So that's useful. For example, when you turn the regulator of your fan and you reduce the speed of the fan, what's actually happening is that if you lower the speed of fan, you are actually lowering the amount of current flowing through that particular circuit by increasing the resistance. Because more the resistance, more the hurdles for the electrons. Sometimes resistance is fixed, it can't be changed. So it's just shown by this symbol. And if it can be changed, if it's in our hands to change it, then we show the arrow as well. This is called a variable resistance, also called a rheostat. It's a device you may see in your laboratories. It looks like this, or at least in the college physics laboratory you will see it. The advantage of using a rheostat is that by changing the resistance, we can change the amount of current flowing, 1 ampere, 2 ampere, 3 ampere. No need to change the number of batteries you are using. Or what if you are using the mains electricity? You can't control the amount of current directly. You can only do it with the help of the variable resistance. And we can do your experiments with it. There are a few more equipments used. What if you wish to calculate how much current is flowing through a circuit? For that we use an ammeter, which will obviously give us the values in ampere, or actually in milliamperes, because ampere is too big an amount of current. And if you want to calculate the potential difference, you use a voltmeter. As I told you, more the potential difference, more is the current flowing through a circuit. It will measure the potential difference in a unit called volt. More about potential difference in section B. This diagram is also double ticked, so you have to practice this. This is a complete diagram showing all the parts. If you buy a cell and it's written on the cell 6 volt, so if you measure it with the voltmeter, you'll get slightly less than 6 volts, but it's measuring the potential difference. But notice that the ammeter is connected in series with the circuit. That means when the current starts from here, the same current flows through the ammeter as well as through the circuit, through the bulb, and the return journey is complete, and that's why the bulb will glow. But this voltmeter is not connected in series. It is connected in parallel to the circuit. Now that doesn't mean that it is mathematically parallel to the wire here. No, it simply means that the current which was flowing through the circuit, when it reaches here, it has two paths. It can go straight as well as it could travel like this. And current will always take all the paths. That means the current will split. Let's say the current was 5 ampere. It's possible that 4 ampere will continue its journey like this, and 1 ampere will continue its journey like this. And of course, they will meet again and become 5 amperes, and the 5 amperes will reach here. But how much current will flow through the voltmeter and how much will flow through the circuit? Well, that depends on the resistance of this part of the circuit and the resistance of the bulb. As I said, if there is traffic coming and there is more hurdle out here, then most of the traffic would like to go straight, and very less traffic would like to take this path because the resistance here is too much. And that's why voltmeters always have very high resistance, so that very little current flows through it. We don't want less current to reach the bulb. We would like the bulb to glow brightly. We just want to measure the potential difference. In that process, why should we steal some of the current? So make the resistance very high so that very little current flows through it, and most of the current goes in the main circuit itself. So this is the meaning of being connected in parallel. There is always splitting of current. Even here, if you see, the voltmeter is connected in parallel, not mathematically parallel, but it's just that the current is splitting into two paths. Whereas the ammeter, which could be connected anywhere, here, it doesn't matter, the entire 5 amperes will pass through the ammeter, and that is why the ammeter should have very low resistance. We don't want the ammeter to create more hurdles for the current in the circuit. The ammeter's job is simply to measure the amount of current flowing through it. In that process, we can't increase the resistance. So now we see 3 differences between them. Number 1, well, ammeter measures the current and voltmeter measures the potential difference. Ammeter is connected in series with the circuit, voltmeter is connected in parallel to the circuit. Ammeter has low resistance and voltmeter has high resistance. But one common thing you can see is that the positive point of ammeter is always facing the positive terminal, and the negative point is always facing or connected to the negative terminal. That is true for voltmeter also. Positive is connected to positive and negative is connected to negative. If you don't do that, it will not give you proper readings. Even here you can see the positive is connected to the positive terminal and the negative to the negative terminal. So when you draw a diagram, make sure you keep all this in mind. This is the key. So is it open or closed? Clearly it's closed. That's why current can flow and the bulb can glow. Rheostat, that's a variable resistance. That means we can change the length of the wire in it, which is a part of the circuit, and basically we can change the resistance. By changing the resistance, we can actually change the amount of current flowing. So when you change the resistance, you will see the ammeter's readings will also change. Sometimes it is 0.5 ampere, sometimes 0.2 ampere, and that's important while doing experiments. There is one more instrument called galvanometer, which looks similar to a voltmeter or an ammeter, but it's used simply to check if there is some current flowing through it and in which direction is it flowing. If you don't know the positive and negative terminal of a cell and we want to know in which direction is it flowing, we can use a galvanometer. It has no positive or negative signs marked, so it doesn't matter how we connect it. And of course, it will be connected in series only, not in parallel. So it will tell you if current is flowing and the direction of current. It can't tell you how much current is flowing. That can only be informed by the ammeter. And finally, the symbol of a bulb. or any other device. It's called a load. Any appliances which is connected is called a load. That's a definition. So the double tick diagrams have to be practiced with proper headings. This one's, these two, not this one. Voltmeter, ammeter, and write the diff 3. This is 3 points. It doesn't mean 3 marks. Next, the difference between insulators and conductors. I've already explained that insulators don't have any free electrons. Conductors, like metals, they have something called free electrons. You see, it looks like this. Suppose this is a copper wire. The outermost shell of copper has some electrons which roam about in the entire wire. They're not stuck to the atom. They are called free electrons. So as soon as there is a potential difference provided by some cell, they become very disciplined. Earlier they were moving haphazardly. Now they will move in a fixed direction from a lower terminal to a high, from a lower potential to a higher potential. Of course, current will still be shown as from positive to negative. So this is how electricity is produced because of free electrons. But I'm talking about a wire. What if it was an electrolyte, like water, tap water? Electricity can flow even through tap water, not pure water. But in tap water, there are no electrons. And how does electricity flow through it? Well, there it is because of ions. But we're not talking about ions in this chapter. So insulators don't have the free electrons. Conductors have free electrons. Another difference is insulators don't allow much current to flow through them, and conductors do. Insulators have very high resistance. Traffic jam, total traffic jam, like in Mumbai. Conductors is like a free highway. So there is a very less resistance. So more current can flow through it. All the examples have to be learned. Human body, your body, unfortunately, is a good conductor of electricity. Good enough, so you can get a shock. Pure water is not a good conductor. Distilled water is not a good conductor. But tap water is, or acidilated water is, because they have some impurities, so ions are produced. Mercury is a liquid, but it's a metal, so it is a good conductor of electricity. Wood, glass, leather, rubber, they are bad conductors, insulators. So that is why we wear rubber gloves while handling electrical equipments. Next, circuits. As I said, we call a circuit closed when the circuit is complete. That is, a path is complete. Look at this diagram here. A metal wire, so conductor, it's a conductor, so electricity can flow. Here, it's a broken circuit. There's an air gap, so electrons cannot jump. Of course, if the potential difference is like very high, thousands of volts, then electrons can even jump through air, and we see it as sparks. That's right, sparks, or even lightning that we see. They're basically electricity through a bad conductor like air, because the potential difference is so high, electrons are forced to travel even through air, a bad conductor. And in that process, they burn the air, and we see it as sparks. Here, they've used a thread, which is a bad conductor. So even this is called incomplete circuit, because electrons cannot flow through it, current cannot flow through it. So there are some numericals which you will have to practice for homework. They are very easy. In solved examples, you have to do just one of them, this one. The rest have to be read, of course. They've given the amount of current and time. Read the question thoroughly, use the formula and solve it. This calculation is a bit challenging, but you need practice. Don't just copy the answer. 10 raised to minus 19 goes up and becomes 10 raised to positive 19. 6 upon 1.6. Dividing by decimals is always tricky, so do it and you'll get this answer. Similarly, here we have some diagrams to be practiced in the exercise itself, so make sure you complete it after reading the question. Here we have 3 numericals. All 3 are very straightforward. Always 2 pieces of information are given and 1 piece of information is asked. So the formula is same. Use it and get the answers.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.